Hi, good morning, good afternoon, and good evening, depending where you are. Welcome back to the Access Seminar. Today, we are very pleased to invite Mrs. Nika Mansouri Ghiasi to introduce her latest research on the storage-centric computing for genomics-related applications. Mrs. Ghiasi is a PhD candidate in the Safari Research Group at ETH Zurich, working with Professor Onur Mutlu. Her current research interests are in computer architecture and bioinformatics multidiscipline, and focusing on the large-scale bioinformatics applications, storage systems, and their interactions, as well as emerging technologies such as ultra-dense 3D integrated systems. Nika has co-authored several works on those topics in major computer architecture venues such as ISCA, ASCLOS, and Micron, as well as major bioinformatics venues as the ISMB Bioinformatics and the Nature Reviews. Moreover, I'm pleased to introduce that as Professor Onur Mutlu's groups contribute to RP21 communication interface and OS architectural support for CPU accelerator heterogeneous architecture, RP22 architecture optimization considering the characteristics of the deep neural networks, as well as RP24 architectural optimization for in-memory CMOS ReRAM accelerator for large-scale neural networks. So many thanks for Mrs. Ghiasi to prepare this talk. With that, I would like you to welcome Mrs. Ghiasi. So let me pass time to Mrs. Ghiasi. Thank you.
Okay, thank you so much for the introduction. Am I audible still?
Okay.
Okay, good. Thanks for so do you hear me and see the screen and everything, I assume, still? Okay. So welcome everyone, and today I am going to talk about storage-centric computing for genomic and metagenomics. And for that, I will summarize two of our recent works in Safari Research Group on storage processing for genomics and in storage processing for metagenomics. So I get started with GenStore, which is a high-performance and storage processing system for genome sequence analysis. So genome sequence analysis is critical for many applications, such as personalized medicine, outbreak tracing, and evolutionary studies. And genome sequencing machines extract smaller fragments of the original DNA sequence known as reads. So we have this whole DNA sequence that gets extracted into these smaller fragments. So read mapping is a fundamental step, which is the first key step on many genome analysis pipelines that aligns the reads to potential matching locations in a reference genome. And for each matching location, the alignment step finds the degree of similarity or alignment score between the reads and the reference genome. Calculating the alignment score requires computationally expensive approximate string matching, or ASM, to account for differences between the reads and this reference genome that could happen due to sequencing error or genetic variation. And then based on the knowledge we gain from these differences, we can do some genomics or medical studies to gain further insights. So genome sequence analysis typically requires performing this expensive computation in large amounts of data. Therefore, the genome sequence analysis is both suffering from computation overhead and large data movement overhead from the storage system. Due to the importance of the domain, there's been a lot of effort into improving performance of genome analysis via various heuristics, accelerators, or filters that prune reads that do not require expensive computation. While these approaches significantly alleviate computation overhead, they still do not alleviate data movement overhead from storage system, whose impact becomes even larger when other overheads get alleviated. So the idea that we had in this work is to filter the reads that do not require expensive computation inside the storage system, so we can fundamentally reduce data movement all the way from the storage system to the rest of the system. Examples of reads that do not require such expensive computation are exactly matching reads that do not need to go through approximate string matching because they exactly match, or non-matching reads, meaning reads that do not have any potential matching locations. Therefore, they can skip the expensive alignment step. However, implementing these filters inside the SSD is challenging because read mapping workloads can exhibit different behaviors based on features of input data set And there are limited hardware resources available inside the storage system. By addressing these challenges in this work, we present GenStore, which is the first storage process system for genomics that addresses or alleviates both computation overhead and data movement overhead. And we show that GenStore provides large performance and energy benefits at low cost. So this was a high-level overview of the talk. Now I provide a little bit more background on genomics for those of you who might not be very familiar with it. So that would be all the sufficient genomic background that we would need for this talk. And after that, we continue. So, we talked about the reference genome and the reads I need to map to it. So the search space in the reference genome can be very large. So for humans, for example, it is more than 3 billion characters. So to facilitate the search within such a reference genome, typically read mappers use a structure called an index that has k-mers, which are subsequences of length k extracted from the reference genome, and the locations that these k-mers belong to. So we kind of have this index structure to facilitate the search. So typically state-of-the-art read mappers consist of 3 key steps in high level. The first step is called seeding, that determines potential matching locations or seeds in the reference genome. So to do that, mappers extract k-mers from the read and look up these k-mers in the index data structure. And for the locations that hit, the mappers mark those locations as potential matching locations or seeds. The second stage is seed filtering. So in this part, which some of the operations performing this step would be chaining. So in this part, what the mappers do is they prune some of the seeds in the reference genome that are likely not high quality matching locations, so that we can reduce the number of locations for which we would do the third expensive alignment step, that for the matching locations that pass through the step 2, for those parts, the mappers determine the exact differences between the read and the reference genome via the computationally expensive approximate string matching that we talked about. So this is a high-level overview of read mapping. So to analyze the impact of storage I/O data movement overhead, we perform a case study on real-world genomic read sets with various read mapping systems and software and hardware, and various state-of-the-art SSD configurations. And we make several key observations, which I will summarize them here. First is that the ideal in-storage filter significantly improves performance by reducing computation overhead and reducing data movement overhead. So given such ideal filter existing, it can significantly alleviate these 2 overheads. Second, having an ideal filter located outside the SSD provides lower performance benefit because it does not reduce data movement overhead from storage system, and also it must compete with read mapping of unfiltered reads for other system resources such as computation and main memory bandwidth. And finally, a hardware accelerator used for read mapping that would address its computation bottleneck further makes I/O a more emphasized and larger bottleneck in the system, because the other bottlenecks are relatively alleviated. So motivated by these points, our goal in this work is to design a storage filter for genome sequence analysis in a cost-effective manner. And to achieve that, we have several design objectives. First is to achieve high performance, so that in storage filtering performance needs to overlap with the filtering, with the read mapping of unfiltered reads, so they can perfectly hide the latency of filtering inside the storage system. And second is to have high applicability, so that it can support reads with different properties and different degrees of genetic variations. And finally, is to have low cost, so that we do not incur significant hardware overhead. So with that, let's go now to the design of GenStore. So as I mentioned, so the key idea of GenStore is to filter reads that do not require alignment inside the storage system with these accelerators located on the SSD controller, and send the reads that will require substantial processing during read mapping to the host system or to an accelerator that's going to perform read mapping. And the challenges are that different behavior across read mapping workloads based on features of input sets and limited hardware resources in the SSD. Now let's take a look at the filtering opportunities in more detail. So sequencing machines that we talked about earlier, they produce one of 2 kinds of reads. One is that short reads that are highly accurate and short, And the other class are long reads that are less accurate relatively, but have much longer length. So reads that do not require the expensive alignment step and thus can be filtered would fit within these two classes in our work. So the first class that we consider are exactly matching reads that do not need expensive approximate string matching. And these are reads with low sequencing error rates, meaning short reads, combined with the fact that the ones that have low genetic variation. For example, humans have relatively low genetic variation. Then the second class are non-matching reads. And these are the reads that do not have any potential matching location after step 2 of read mapping. So they can skip this third alignment step. And these are the reads with high sequencing error rates, which would happen in long reads, or reads that are short or long, but then have high degree of genetic variation. For example, viral or bacterial samples some of the reads can fit within that category because of their high genetic variation. So therefore, we have two sets of designs here, GenStore EM for exactly matching reads and GenStore NM for non-matching reads. So now let me get started with a brief overview of GenStore EM. So it is an efficient and storage filter for reads with at least one exact match in the reference genome. And it uses simple operations without requiring expensive alignment. But the challenge is that to find these exact matches, although we don't need expensive computation, we still need large number of random accesses per each read to the reference genome and its index. And it is difficult to have to support these random accesses inside the flash chips. They're relatively, it's a lot more challenging to handle it. And also the DRAM capacity we have inside the SSD is also limited. Let's say for a 4 terabyte SSD, we would have 4 gigabyte of DRAM. So it is very small. So it cannot hold all the index and reference genome to support efficient random accesses. So to address this challenge, we have these ideas that I'm going to discuss. The first one is read-sized k-mers to reduce the number of accesses per each read. So typically we have a read, and as I discussed, we have these k-mers extracted from it. In our work, we include or we consider the whole read as one k-mer. So therefore, to look up this k-mer, we only need one index lookup per read. So we already reduced the number of accesses. Then, since we know what each read will be accessing, how each read will be accessing the index, we can already avoid random accesses by sorting these reads already. So that would turn all the random accesses to sequential scan of the read set and the index, which is a lot more efficient to handle inside a modern SSD. So let me dive into this with a little bit more detail with a small example. So I'm here showing a small read with 10 characters. In reality, short reads can be few hundred bases, but for simplicity, I'm showing here the smaller read. So here, the first data structure we have is sorted read table. So the read set that we have is already sorted and with the IDs of the reads. And the other data structure we have is sorted k-mer index, which has read size k-mers, as I'm showing here, and the locations of these k-mers. So these k-mers are much bigger than the original k-mers typical read mapper would use. And of course, both of these data structures are sorted. So let's see how an exact match can be found in this with these two simple data structures. So here we have a comparator. We compare, so if read and k-mer are equal, we know that it's an exact match. It can be filtered from further analysis of read mapping and alignment. Then we go to the next element in these two. Okay, so if the read is bigger than the k-mer, here I'm showing sort of alphabetically, right? So then we realize that we need to go look up the next k-mer because they didn't match. And then here in this case, we look up the next k-mer, we realize already the read is smaller than the next k-mer, meaning that read already did not match to any of the elements in the k-mer index. So we realize that that read is not an exact match, therefore it needs to be sent for further analysis in the read mapping pipeline. And then we go and check the next read. So the simple structures avoid random accesses to the NAND flash chips, and it can find these exact matches using very simple and low-cost logic. So as I talked about in this index, we are storing read size k-mers. So the k-mer index takes a large amount of space. So it can be 126 gigabyte for a human index, whereas originally it could have been around 5 to 7 gigs. So due to the larger number of unique k-mers, so when the size of the k-mers increase, therefore we of course have a larger number of unique k-mers, and the k-mers themselves are also bigger. So to alleviate the size overhead of this k-mer, we have this idea of replacing the k-mers themselves with the strong hash values that represent the k-mers. So that would shrink the size of this table a lot, by around 4 times. However, it is still to some extent larger than the baseline index that the typical read mapper would use. But we find in our work that this is the right trade-off to make for the context of storage processing, because it is trading off this slightly larger storage space to achieve much better performance by more suitable access patterns. Okay. And then here's a simple design, a very lightweight design. So we have these two tables, the table and an index here stored in a flash array. They are uniformly distributed across different channels so that we can achieve the full internal bandwidth of the SSD. And yeah, as I mentioned, it's like evenly distributed. And here we have these lightweight hardware, the comparator on the SSD controller. So then we have these data being read and just simply going through the comparator and going to the host system for further analysis. So step 1 and 2 can be pipelined. So therefore, during filtering, while some batches of reads are being filtered, Gestor EM sends the unfiltered reads to the host system. So for the other batch, the analysis can already move on. And that enables overlapping the execution of filtering inside the SSD and the mapping inside the host system or a mapping accelerator. So I very briefly, like in a lot less detail, discussed Genstor NM. So as you remember, we had this second step that is that was seed filtering or chaining. So Genstor NM is an efficient chaining-based storage filter to prune most of the non-matching reads. So however, it is so challenging to perform full-fledged chaining inside the SSD because for a read with and seeds, we need to perform a lot of different operations to perform this dynamic programming that the chaining operation requires. So this costly dynamic programming on many seeds in each read particularly becomes challenging for long reads with many seeds. So that will require both large computational resources and large buffer spaces for buffering all these seeds. So therefore, we use in Gestor and we design a lightweight chaining filter. So our idea here is to selectively perform chaining only on reads with a small number of seeds, and directly send the reads that require more complex chaining to the host system. So we do not oblige ourselves to perform all the chaining operations in the SSD, only for the reads that have a small number of seeds. But that is, so this is based on this observation that I'm going to talk about. Here in this plot on the y-axis, we see the alignment probability, meaning the probability that the read would actually need to go to alignment stage. And on the x-axis, we see the number of seeds per read. And for many different data sets, so I'm here showing one example, but for across different species, also we observe that for reads that have large number of seeds, it is actually highly probable that they would actually go to the alignment step. So they do not get filtered through chaining anyway. Therefore, reads with sufficiently large number of seeds are very likely to align, and they do not need to be going through the chaining filter. So that simple lightweight chaining filter that we have in SSD for reads with small number of seeds already filters many of the reads that would not align without requiring costly resources inside the SSD. For more details about its design, I invite you to check our paper. I briefly go over the evaluation. So we experiment with different types of read mappers. Here base, it refers to state-of-the-art software or hardware read mappers for short or long reads. And GS in this case refers to base vulnerabilities integrated with GenStore to assist it with the filtering operations, so that we see how much additional benefits GenStore provides on top of the state-of-the-art read mappers. And we have various SSD configurations with lower, medium, and higher bandwidth, so that we can cover the range of benefits that GenStore provides for different types of SSDs. Okay, so for read sets, here I'm showing for a human data set with 80% exact matching reads. So for software mapper and hardware mapper, we are observing that for the software mapper, it has 2.1 to 2.5 times speed up. And for the hardware baseline, it has 1.5 times to 3.3 times speed up additionally. And so on average, it has 3.9 times energy reduction. And here I'm showing the analysis of GenStore in M. And we observed that it has 22.4 to 27.9 times the speed up compared to the software baseline, and up to 19.2 times the speed up compared to the hardware baseline, on average 27.2 times energy reduction. And we measure the model area and power overheads of GenStore based on a synthesis. And here I'm showing for an 8-channel SSD that it incurs only 0.006% of 14 nanometer Intel processor when it's skipped down. So I'm just showing it for a comparison point. And less than 9.5% of the 3 ARM processors in a simple SATA SSD controller. So even on a nice SSD controller, the only considering these 3 ARM cores, relative to them, the area overhead is this much. So there are many more analyses in the paper that I would like to invite you to check if you're interested. So we have a lot of sensitivity studies, performance benefit of GenStore. What if all these designs are implemented outside the storage system? To what degree they provide benefits, and to what degree there's still a gap? And also more detailed characterization of all of these reads and mapping behavior for different inputs with different species. So yeah, here is again so our paper. Okay, sorry. So then for the conclusion, I briefly go over it again. So there's been significant effort into improving read mapping performance through various techniques, but the problem is that while they address the computation overhead or memory overhead, they do not alleviate data movement overhead from the storage system. And our goal in this work was to address this overhead to improve performance of genomics. And the idea was to filter reads that do not require expensive alignment inside the storage system to fundamentally reduce data movement overhead of genome sequence analysis. And there were different challenges, such as different behavior across read mapping workloads and limited available hardware resources in the storage system. And to that end, we proposed GenStore, which is the first in-storage processing system designed for genome sequence analysis to reduce both the computation and data movement overhead. And we, as we discussed, show that GenStore provides large speed up and energy reduction at low hardware cost. So that was an overview of my talk. I assume that I will go through the next presentation, and then after that, if there are any questions, I would take it. Okay, so I assume that is the case. Now, we go to the next work, which is MEGIS, high performance, energy efficient, and low cost metagenomic analysis within storage processing. Okay, so I provide a brief background on what metagenomics is, because we talked about genomics right now. So now we're going to see what are the differences and so on. So metagenomics is a study of genome sequences of diverse organisms within a shared environment. That can be like blood, ocean, or soil. So it overcomes the limitations of traditional genomics because it bypasses the need for analyzing these individual species in isolation, which is not possible in various use cases. For example, the ones that require analyzing complex microbial samples that are residing in human gut or in ocean or in soil. So it's not possible always to isolate these species and culture them separately in a lab when they're within that complex environment. So metagenomics enables the analysis of those genomic components even within such complex samples that are very frequent actually in the world. So therefore, it has led to groundbreaking advances in many fields, such as precision medicine, understanding microbial diversity of an environment, or discovering early warning signs of communicable diseases. So since the species that are present in a metagenomic sample are not known in advance, metagenomic analysis typically requires performing several tasks that will lead a deeper understanding of the composition of the species within the sample. So here I'm showing this DNA sequences of various organisms in the sample. So the first step is preparation of input queries. Again, we extract k-mers out of the genome sequences of these organisms. And the second step, which is presence-absence identification, looks up these k-mers within a large database containing information on many species. And these databases can actually be very large, even surpassing 100 terabytes in some of these emerging databases. So, and at the end of this stage, we have the IDs of the species that we find to be present in the sample. And the third optional step is abundance estimation, which finds the relative frequencies of these species in the sample. Okay, so with that background, now we go through this motivation part. Since metagenomics requires accessing large amounts of data that originally reside inside the storage system, we perform a case study of performance of metagenomic analysis tools with various state-of-the-art SSD configurations. And here I'm normalizing their throughput compared to a hypothetical case with zero IO overhead. And we are showing here that with both performance optimized and cost optimized SSDs, IO data movement causes significant performance overhead in metagenomic analysis pipelines. Further in our analysis, also we show that IO becomes an even larger overhead in systems when other bottlenecks such as computation and main memory are alleviated. Since IO overhead due to accessing large amounts of low reuse data is hard to avoid, so one might think it is possible to avoid it, let's say, by these solutions. First is the sampling techniques to shrink these database sizes. However, such solutions reduce accuracy to levels that are unacceptable for many accuracy critical use cases. And other potential solution might seem to be keeping all required data by metagenomic analysis completely and always resident in main memory, but such a solution is energy inefficient, costly, unscalable, and unsustainable. And this is due to two reasons. First is that database sizes that are already large, they increase rapidly. So for example, in many cases, they double in size every few months because of the new species that get discovered and added to the databases, or many different databases that keep including richer and richer information. And regardless of individual sizes of databases, different analysis need to access different databases. So keeping all of them always in main memory becomes unsustainable. So motivated by these points, our goal in this work is to improve metagenomic analysis performance by reducing large data movement overhead from the storage system in a cost-effective manner while maintaining high accuracy. So while in storage processing can be a promising direction to address this overhead of data movement from the storage system, it is challenging to adopt it in this case because metagenomic analysis tools cannot directly be adopted to the storage environment due to the limitations of SSD's hardware, for example, latency of NAND 5 chips, limited DRAM capacity inside the SSD, and limited bandwidth of this DRAM inside the SSD. So in this work, we address these challenges as we discussed, and we proposed Ghiasi, which is the first in-storage system for end-to-end metagenomic analysis. And the idea here is to enable cooperative in-storage processing for metagenomic analysis, which is enabled by a hardware-software co-design between the storage system and the host system. So let's see an overview of Ghiasi's key steps. So step 1, preparation of input queries. Step 2, presence absence identification. And step 3 is abundance estimation. To effectively leverage these heterogeneous resources, meaning the storage system and host system, to perform these 3 steps, we do hardware-software co-design in different directions in our board. So first is task partitioning and mapping, such that each step executes in its most suitable system. So to that end, we run step 1 in host system and step 2 and 3 in the storage system. We will discuss in a little bit more detail why in the next slide. Second is a data computation flow coordination, so that we can reduce communication overhead between different parts of the application that are partitioned in different parts, and also reduce the number of writes to the flash chips. And third is storage-aware algorithms, so that we can enable efficient access patterns to the SSD. Fourth is lightweight in storage accelerators, so that we can minimize the required SRAM or DRAM buffer spaces needed inside the SSD. And finally, data mapping scheme and flash translation layer FTL specialized to the features of metagenomic analysis, such that we can leverage SSD's full internal bandwidth while performing in-storage processing steps. So now let's take a closer look at step 1, preparation of input queries. Megas employs sorted data structures to avoid expensive random accesses to the SSD. So to enable that, Megis needs to extract k-mers from the sample and sort these k-mers. The database is sorted offline. So I want to actually clarify one point. In GenStore, the read sets were sorted offline. Here, in this case, we cannot do sorting offline because we are not sorting the reads, we are sorting the k-mers. So the k-mer space usually explodes the volume of the data that needs to be stored. So if we have some read set and then extract k-mers of them, then we will need to store significantly large k-mer set alongside each read set, which would be very inefficient because like the reads, you have many different read sets, and for each of them, you cannot store separate, much larger k-mer set. Whereas for GenStore, the size of the read set would more or less remain the same. So it had to go through the sorting process. It could happen offline, and it would not hurt the throughput of data preparation. But here, since we work with k-mers, sorting needs to be handled online. So Megis executes this step inside the host system because it benefits from larger DRAM or more powerful computation available inside the host, and incurs fewer writes to the NAND flash chips than the case that we would have run this inside the SSD. And running this step inside the host system enables overlapping this step with the step 2, which, as we will discuss, will be running inside the SSD. To execute step 1 efficiently inside the host system, Megis needs to avoid significant overhead due to data transfer between the steps, and also minimize performance and lifetime overheads, even when host DRAM cannot hold all query k-mers. So for a reasonable sized DRAM and a reasonably large input set, the extracted k-mers would fit in the DRAM, but even that is not the case in systems with smaller DRAM. We wanted to ensure that we do not incur performance or lifetime overheads due to excessive page swaps. So let's take a look at step 1's design now. So after extracting these k-mers out of the input read set, so here the idea is to divide k-mers into independent partitions based on their alphabetic range. So this enables overlapping operations on different partitions. So that means we can overlap step 1 sorting, performing in one partition with data transfer to SSD, and step 2 in storage operations on the previous partition. So that enables already to hide this data transfer and these operations to be overlapped and their latency be partially hidden. So after this step, we go to step 2, which is the presence-absence identification. So in this step, we identify the common k-mers between the query k-mers and the database k-mers. And for these common k-mers that we found, we retrieve the IDs of the species so that we find out which species they belong to. So Megis executes this step inside the SSD because it accesses large data with low reuse, and it involves only lightweight computation. To execute this step efficiently in the SSD, Megis needs to leverage internal bandwidth of the SSD efficiently and not require expensive hardware resources such as large DRAM bandwidth or large DRAM capacity and costly logic units. Here, to discuss the designs, I first want to emphasize this challenge. So reading all these k-mers from the NAND flash chips to the internal DRAM, and the query k-mers from the host system, and buffering the intermediate results so that it can be used in the next step. All of these pressures the limited internal bandwidth of the SSD. So to address this challenge, we employ a technique to compute directly on the NAND flash data streams. So therefore, we do not require to buffer all the data at the same time, so that we can stop limiting this bandwidth that we have for DRAM inside the SSD. However, while we are not using DRAM to buffer these k-mers, we still therefore need to have per channel buffers device. So the second point that we do is that we reduce the buffer size based on detailed analysis of features and access patterns of the application. And by specializing these buffer spaces based on the application, we manage to perform these in storage processing operations requiring only 2 registers with the size of each k-mer per each channel. Therefore, this step 2 can be performed with minimized hardware resources in the SSD with these small registers. And finally, we have these common k-mers stored in the DRAM, so that in the part 2 of step 2, we retrieve the IDs, species IDs of these k-mers. So Megis retrieves the species IDs of these common k-mers by looking up a sketch database. The sketch database stores these representative k-mers or sketches of different species and the IDs of the species that these k-mers belong to. So when we want to encode many different species in a very rich metagenomic database, such a simple approach of storing the database becomes space inefficient. There are different works to improve the space efficiency of such a data structure. For example, using various steps of tree structures to make it a lot more space efficient. However, such an approach as adopting them inside the SSD is not efficient because, and it's very slow because of the long latency of NAND flash chips, because these data structures require pointer chasing operations. So having long latency would delay these whole pointer chasing operations significantly and becomes very inefficient. So therefore, in our work, we try to come up with a more suitable trade-off, which is fit within the storage processing paradigm. And to that, we come up with data structure, which we call k-mer sketch streaming. It is not as space efficient as the state-of-the-art space efficient solutions. However, it is still significantly smaller than this baseline approach that I showed. However, we find k-mer sketch streaming approach is a much more suitable trade-off and design for storage processing because it enables finding all the IDs using only streaming accesses. So more details about how exactly this data structure is formed are in our paper, which I again invite you to check. Similarly, more details about this optional step 3 are also again in the paper. And again, also Megis FTL. So please check if you're interested. I briefly summarize our results. So we model performance, energy, and power based on latency, throughput, and power of hardware and software-based components. And we have various baseline comparison points. So performance optimized software baseline and accuracy optimized software baseline, and a PIM hardware accelerator tool that uses processing in memory to further improve the performance of the performance optimized baseline. And we have our analysis on different SSDs, a cost optimized SSD and a performance optimized SSD, so that we can understand how Megis provides benefits in different system configurations. So here in this talk, I'm going to show the results for the use case of finding a species that are present in the sample. For the abundance estimation task, which is another important metagenomics task, more analysis can be found in the paper. And we perform this analysis with metagenomic samples with varying degrees of genetic diversity. So here I'm showing speed up over software baselines for cost optimized SSD. So we show that for both performance optimized and accuracy optimized baseline, Megis leads to large speed up. And here we repeat the same analysis with the performance optimized SSD and observe that we make the same observation that again, Megis provides large benefits in this context as well. Here I'm showing speed up over the PIM hardware baseline for cost optimized and performance optimized SSDs, and show that Megis improves performance significantly compared to this PIM baseline. And in this plot, I'm showing the average energy reduction across different input street sets and different SSDs for performance optimized, accuracy optimized, and PIM baseline, and show the large energy reduction that Megis provides. And I would like to here emphasize that Megis provides the same accuracy as the accuracy optimized baseline, so by providing all these benefits. And our more detailed analysis also shows that its accuracy is in fact significantly higher than the performance optimized and the PIM baseline. And these benefits are achieved while incurring only a small area overhead of only 1.7% of the area of the 3 cores on the simple SSD controller, and 4.6% of their power consumption. So this is power consumption only for these SSD controller cores, meaning it's relatively very small. So now I would like to also show one final result, which is about the impact of Megis on system cost efficiency. To do that, we analyze these systems on a cost-optimized system, which has the cost-optimized SSD and 64 GB of DRAM, and the performance-optimized system, which has the performance-optimized SSD and 1 TB of DRAM. And here I am showing performance of the baselines, the performance optimized and accuracy optimized baselines that are running on the cost optimized system and on the performance optimized system. We show that comparing Megis. So, and here I'm showing also Megis performance when running on the cost optimized system. So here we see that when they run on the similar types of system, meaning all of them running on the cost optimized system, Megis provides large benefits. But moreover, we also show that Megis outperforms the baselines even when running on a much less costly system. So as you see here, the performance optimized and cost optimized. So performance optimized and accuracy optimized softwares are running on the more expensive system and still are performing worse than Megis while running on much cheaper system. So based on this observation, we see that Megis improves system cost efficiency, which we hope it would lead to making adoption of accurate metagenomic analysis more accessible. So there are many other results in the paper, which I am just going to skim through them. So what if we just run these functionalities on existing cores on the SSD controller? What if we have the exact same optimizations outside the SSD and many different sensitivity analysis? And also, as I mentioned, Megis says performance for different measurement use cases. And here is the link and information to the paper. And again, a brief conclusion. So metagenomic analysis suffers from significant storage IO data movement overhead. And in this work to address this overhead, we propose Megis, which is the first in storage processing system for end-to-end metagenomic analysis and leverages and orchestrates processing both inside and outside the storage system. And it leads to large performance and energy benefits while achieving high accuracy and incurring only small costs. So yeah, I thank you so much for listening, and that would be all. If there are any questions from anyone, I would also be happy to answer.
Any questions? So maybe I have a small question. So thanks for your introduction and your amazing results. So my question is about your first work about the non-executive matching. So in the results, you show that you will be a more than 20 times speed up, which is a amazing result. So my question is there any sacrificing of accuracy because it's a non-executive matching? So in this result.
Yeah, so it would not lead to any accuracy degradation because it would filter reads that definitely would not have any. So compared to the baseline read mapper, compared to the most accurate baseline read mappers, it would lead to the same accuracy because they would also filter the same reads because they would not find the potential matching locations. So in that case, it would, regardless of inside or outside storage, the same reads would be filtered. So relatively no accuracy loss is incurred in that case.
Thank you. So
Sure.
another question is, so about this genomic and metagenomic basis, so how large the data? I think all your work are focusing on the external memories from the SSE. So I believe the total data for those processing are very huge, but I have no idea about it. Can you introduce a bit more? The computation capacity and also the scale of the data, as well as the relation between the task, the analysis tasks versus the data, total amount of data. So can you give us some more ideas? Thank you.
Yeah, sure. So maybe I can start with the metagenomic case here. So for that, the databases that we are dealing with, they can be very large. So in some recent examples, as I said, they are above 100 terabytes can be size of a single database. But of course, even regardless of that, different analysis will also require access in different databases, even if they're smaller. And the other point is that the microbial diversity of the earth, of course, is very large, and we do not know more than 99% of the microbes currently existing on the surface of the earth. So the rate at which now we are discovering them, adding them to databases is very fast. Therefore, already these databases that are already that are large are increasing in size very quickly. And as I mentioned, over the course of a few months, they double. So these big repositories or databases are growing very fast. So in-storage processing provides at least a more scalable solution to deal with this growing data. And so that is about the data sizes. But another fundamental point is the low reuse of the data. So that actually, maybe I can provide this example more clearly with the GenStore case. So for GenStore, we are filtering the read sets. So you can have different read sets, different samples that are coming to be analyzed. And a lot of them actually do not need to be analyzed very extensively because they would be sooner or later filtered. So if a read is going to be filtered and therefore has very low reuse in its computation patterns and its access patterns, it is more efficient for it to be analyzed and pruned as early as possible in the system, because and that would be even regardless of the size. Of course, like this benefit would be more pronounced when we work with large scale genomic data, but even regardless of the size, if the data has such low reuse and can be excluded, when it is done inside the storage system, it saves both the external bandwidth of the SSD and also does not compete with the main computation for reads that are not pruned for resources such as memory bandwidth and computation. So it's kind of like, I think these touch into different aspects of the benefits that in-storage processing provides for genomics and metagenomics, both database data sizes and the reuse pattern.
Yes, thank you.
Sure.
So is there any other questions? Okay, so maybe we need some more time to digest the novel knowledge in this area. Is rather amazing and interesting. So hopefully we could continue our discussion offline. So for the time limit, we have to wrap up this seminar. Many thanks to Nika to give us this excellent talk. Thank you. So
you're welcome, and thanks for listening. Thank you for your time.
you. So here for our next seminar, we will hold the seminar on September the 19th. We will invite Mrs. Zixi Jing, PhD student with the Department of ECE HKUST to give us a talk. So please stay tuned and see you next time. Thank you. Thank you. Bye.